Good morning, everybody. Welcome to this second day of lessons of our INSPYRE, our international school on modern physics and research. Today we will have two lectures. The first from Professor Fabio Sciarrino of Sapienza University of Rome, and he's giving a lecture about the quantum mechanics and about its technologies. So, Fabio, please.
Thank you. So good morning and good afternoon to everyone. It's a pleasure being here. And so my goal of today is to observe with you how starting from the beginning of quantum mechanics of the last century, we can then go to today research effort on the so-called the second quantum revolution. So we will combine two different pictures, one on the foundation of physics, on quantum mechanics, and the second one on how today we are trying to fully exploit the strangeness of quantum mechanics in order to develop a new technology. As a starting point, let me start from the following video, which has been released by Microsoft a couple of years ago. And this video is somehow summarizing the efforts of Microsoft in order to develop a quantum computer. This will last 1 minute, then we will go back to the last century.
When we talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We can attack global warming.
Security.
What are the boundaries of machine learning?
Fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast, and we're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
Hi to everyone. So this video is how Microsoft is presenting itself in the challenge to develop a quantum computer. Then as following step, we can see the following newspaper highlight, which I've taken from the October 2019. And this newspaper highlight reports the claim of Google done in October that for the first time achieved quantum supremacy 3-4 months ago. So this is where we are now. This is what's happening today. Now we would like to have a jump in the past, once 100 years ago, go to the beginning of the previous century and see how quantum mechanics was developed and what are the real strangeness of quantum mechanics. So this is today we go back to the past, and then we can go back to the 1927. And we can start from the following picture. So this is a very famous picture of a very fundamental conference which was held in Belgium, in Solvay, in 1927. And I guess you can see here many Nobel Prize winners. Let me mention a few of them. You have Marie Curie, Einstein, Planck, Bohr. All the person here are the so-called founder of quantum mechanics. Quantum mechanics was a real revolution, which was developed in a few years. It took something like 10, 20 years to develop the theory, which was really changing the way we conceive our reality in our everyday life. So you can see here some, as I said, fundamental names. We will then go back to Einstein, to Schrödinger, to Bohr hereafter. And so why is quantum mechanics so fundamentally different from classical physics? This is what we are going to see in the next minutes. So my goal is to describe you a very fundamental experiment on quantum mechanics, the two-slits experiment. We are going to discuss together how this experiment happens and which kind of conclusion we can draw from these first key ingredients. So what is quantum mechanics? So when we talk about quantum mechanics, what we introduced when we compare to classical physics is the concept that energy, like matter, are all quantized and they are all formed by elementary quantities. This is quantum theory. All processes of interaction between bodies are quantized. We have elementary particles, such as electrons, atoms, and specifically today, we will discuss about photons, the particle which constitutes the electromagnetic field, that is the particle of light. As I said, I would like to really start describing you one key experiment. Then after this description, we can go to the question time. But let me consider a very simplified description. And our goal is really to understand one of the ingredients of quantum mechanics. And this is the ingredients that then we will exploit when we want to carry out quantum technologies. So you can consider the picture that you have in the slide. You have a source. This is a source of single particle. This single particle may be photons, for instance. This can be a light source, very tiny. This could be electrons. And this source is emitting one particle per time. In my picture, this red ball. This may be one photon. Then you have a wall, and this wall has two holes, the hole A and B. And after the wall, you have a screen, the black screen, where you can detect the particle. And as first step, we can consider this wall, and we put a shutter which block one hole. This means that you have only one hole left along the position A. Then what you do, you carry out an experiment where you send one particle per time, and this is what you can see in the following animation, in the following movie. You have the particle is propagating, it's passing inside this hole, and then it's finally detected at the final screen. You repeat the experiment many times. You always have one particle per time. The particle propagate, the particle will spread, will be detected at the end. You repeat this many times, and then at the end, you will have some probability of detecting your particle. And this can be represented in the following way. Only the hole A is open, and as you may see from the slide, you can see with my pointer, here is where you detect the particle, all nearby the same position. And here you can see what is the probability of detecting the particle. And this probability will depend likely from the geometry of the experiment. And this was the first step, when only the particle could travel along the path A, corresponding to the hole I'm now highlighting. What is now the following step? We block the hole A, we open the hole B, and we repeat again the experiment. We repeat the experiment many, many times. We then detect again the particle. We do this always one particle per time, and this is at the end what we obtain. You see now what are the detected particles when only the particle can travel along the path B. Again, you repeat the experiment many, many times. A key part of the experiment, and you have to perform the experiment one particle per time. At the end, what happens? Something similar to the previous results, only the path B is open. You detect your particle on the screen, and you can then extract the probability to detect the particle B on your screen. And this is now the second step. Now, the third step, that to ask yourself, what happens if now you open both the path A and the path B? What do you expect classically? By classically, it means what is your intuition? You are sending one particle per time. This particle is indivisible. This means that your particle can only go via the path A or via the path B. You now detect your particle on the screen. If you have a so-called classical behavior, you will have the particle traveling either along the path A, either along the path B. And now what is the probability to detect the particle on your screen? It will be the sum of the two probabilities. And this is now depicted in the screen. Because what you can have is that if you go along the path A, you will recover the previous probability, PA. If you get along the path B, you will recover the previous probability, PDB. And then your probability will be the sum of the two. This is what you expect classically. Because classically, you consider only the case where the particle should go either along A, either along B. But now, if you do the particle, this experiment in a quantum regime, what you observe is a so-called quantum interference. What you see now, experimentally, is something like the one that is reported in the slide. You have the particles which are all combined in some position, as shown here, while other position here, you never observe some particle in this position of the screen. So you should really try to consider this example in details to see how could I observe this kind of behavior and not this one. Let me repeat, this behavior is what you obtain if the particle is going along A, and then you expect to observe what you had before, or along B, and then you combine the two cases. But if you do this experiment in the quantum regime, what you observe is the following feature. You have this kind of interference effect where some possibilities are not allowed, while other probabilities are amplified. And now the key question is how can we conciliate this observation with the fact that the particle must propagate along A or along B? So we then have a fundamental question. Which slit does a photon propagate inside? And the answer is like if the photon and the traveling along both paths. So I would propose you to stop here now for the question time. I really would like that you brainstorm on this experiment that like you have already seen in your life, and any question is very welcome.
Fabio, for the moment, I don't see any question about this. So either our students are well acknowledged about the two slits experiment, or maybe they need some time to get less shy. So I propose you to go on. Probably questions are going to come later during the talk.
Thank you, Danilo. So this is the background that you likely have already seen. Let's go on the following step. So let's try now to ask ourselves how we can then describe a particle which at the same time is propagating along path A and path B. And the way we write this in quantum mechanics is with the following expression. I apologize, photone is writing in Italian, it's obviously photon. And what you see here is what we call the wave function, which describes the system. You have this strange symbol here that we call ket, which describes a wave function of the system. And what we say is that within this experiment, what we have is the coexistence of a photon which propagates along A and the photon which propagates along B. And the way we describe this behavior is with the following expression that we will also exploit in the next slides. What is relevant is that quantum interference, according to Feynman, Nobel Prize, and really one of the inspiring physics of the last century, is that quantum interference represents the earth of quantum mechanics. In reality, it contains the only mystery which fully is inside this theory. So let me also try again to compare, to try to summarize a comparison between classical physics and quantum physics. In classical physics, we are used with not coexisting reality. A particle can travel along the path A or along the path B. What tells you the experiment of the two slits is that in quantum physics, a particle can travel along path A and along a path B. And then what we have is that we have a kind of superposition state of the two trajectories. And as I told you, the way we describe this is by using the wave function. So we can write the wave function as photon in A plus photon in B. So this was the introduction. And now let's go to the following step. So now let's see, okay, but we really ask ourselves, where is the particle traveling? So we can imagine to devise a new experiment where we try to use a very sophisticated technology to track what is the path taken by the particle. And in the following animation, this tracking system is represented by this green apparatus here. So now we can imagine that this red ball are atoms or electrons which are propagating, and we try to implement this very peculiar apparatus, the green one, which is trying to extract the information on the path undertaken by the particle. I'm not now focusing on how you can do this experiment, but the key point is that you can try to do this experiment with the better available technology. And really your goal is to say, okay, I do not believe that the photons can travel both at the same time along particle path A and path B, so I can try to record what is the path undertaken by the particle. So what you do now, you can do this experiment, and what happens is that if you do this experiment where you try to observe what is the path undertaken by the particle, again, what you observe in the screen, it's again a classical behavior. This means that by extracting the information on the path taken by the particle is now again behaving in a classical way, where the probability of this joint experiment, where the two paths can be undertaken, is simply the sum of the probability where you have only the path A open and the path B open. So what you can extract from the following experiment is that indeed the reality is also created by our question. This means that the path of the particle is changed by the fact that you extract information on how the system is evolving. And a way to simplify this concept in only 3 words was introduced by John Wheeler: it from bit. What means it from bit? It represents the reality, while bit represents the information. And it from bit means that the reality is a consequence of the information that you acquire on the system itself. And this is a bit counterintuitive, because in our everyday life, our approach is that the reality is existing independently from our observation. And so within our today vision, it's a bit which is deriving from the it. The information is deriving from the reality. I would suggest that now we can now have another very short question session, if there is any request of clarification on this first 20 minutes.
Yes, Fabio, we have a couple of questions. So, Emmanuel is asking, how do you send one particle at a time?
So thank you for the question. So this is peculiar. So let's consider the first simple scenario, where our particles are photons. Photons are the particle of light. So if you see my room here now, in my room there are billions of photons. This means I need to have a very, very attenuated sources. I will take a lamp, or I will take a laser, and in front of the lamp I will put many filters that will reduce how many photons are propagating. I like screening my sources until on average I will get only one particle, one photon per time. This means that typically this experiment are done in the dark, in a lab, where you don't have any background light. You will get one photon per time, and then you will at the end detect one photon per time. And detecting one photon per time requires some very expensive and sensible CCD camera. It's pretty similar to your mobile phone, but they are much more amplified.
Okay, thanks. Then Lorenzo is asking, what happens if the number of slits is 3 or anyway more than 2?
Thank you so much. This is a very good question. So everything gets much more complicated. So what you will have, if you have, for instance, let me try to use a slide to describe. So can we share the screen? And let's try to imagine this experiment. So I have my source here. Again, my source is emitting one photon per time. And now the question is, what happens if I have a wall, and in this wall I have now many slits? You asked about 3, but you can have more. Now what you can have, that you imagine I'm here representing the single particle which is impinging on the wall. Now what you will have, that you will have somehow a superposition of the particle propagating along the hole A, the hole B, the hole C, the hole D. And all these different possibilities will all interfere together in an even more strange way. How we will write down the wave function of such a system? It will be photon in A. Again, I'm exploiting this wave function formalism plus photon in B plus photon in C. And then we will extend this to all the possible slits. And then you will have a screen at the end. Let me draw the screen. This is my screen where I'm detecting the particle. And we detect the particle on the screen. All these possible paths will interfere together. And what you will get here will be something much more complicated, where you will have something like this. I'm drawing the probability of detecting the particle. And this fringe figure is called like that. This is a probability. And this probability will now arise as a consequence that all the possible path propagation will all interfere together. So I hope to have properly addressed your question.
Okay, then there are a few questions that I can summarize together. They all concern the fact that, I mean, if you can clarify how the physical system changes when we disturb the observation. So, for instance, why there is no interference when we observe in which slit the particle passes, or how can we change the system with our observation?
Thank you, Danilo. I guess this is very useful. So let's again try to answer this by using a slide as support. So let me try again. We were considering the following experiment. We had a photon, we had a double slit. I'm spending a lot of time on this experiment because you really have to understand the earth of this experiment. If you understand this experiment, half of our job has been done. So I've written this. This is experiment I've described you before. And what is the wave function here? I told you it's photon in A plus photon in B. This is again the screen that we had before, where we could observe the interference. And then I told you, no, but now I don't believe the photon must go either via path A, either via path B. So I try here to observe, to measure the particle. Obviously, if you have a single photon, it's not trivial, but this particle maybe is not a photon, it's an atom. So I try to measure, and what happens that when I measure, instead of having this state, which I've written as photon in A plus photon in B, when you observe the system, you have what we call in quantum mechanics a collapse of the wave function. You don't have any more photon in A plus photon in B, but you became either photon in A or photon in B. So the observation removes this, what we call linear superposition, and made your system to collapse only on one of the two contributions. And this is the collapse of the wave function, which is induced by observation. This is not intuitive at all. So this is typically studied during the third-year quantum mechanics course in the Bachelor of Physics. And really, the concept of collapse is a very elusive concept for us. But it's the only way to make the theory of quantum mechanics in full agreement with any experiment. So to summarize, you observe your system. Your system was in a superposition. The observation makes the system to collapse in only one of the two contributions. And then since now you have only photon in A or photon in B, all your interference effects are disappearing. Thank you again for the question, because this allowed me to go a bit more in details on that point. Thanks.
Okay, I think we can go on. Then if other questions will arise, we can answer later.
Thank you, Danilo. So we are back. So what I tried to convince you is that the reality, the it, arises as a consequence of the information that you extract from the system. And this is a very fundamental point. Indeed, Einstein was asking, is there a moon in the sky if I don't look at it? So is the moon existing by itself, or is the moon existing as a consequence of my observation? And this, so it's strange because Einstein was one of the fathers of quantum mechanics, but somehow he was disagreeing on the extreme consequence of the theory. The consequence that he could not accept that quantum mechanics is a theory which is intrinsically probabilistic. You cannot predict some observable with certainty. And this intrinsic probabilistic feature of the theory was unacceptable for Einstein. And it's very well known, its sentence, God does not play dice. And by this sentence, what Einstein wanted to express, that Einstein still believed in a theory that could be fully deterministic. So as I told you, quantum theory was developed between the 1905, the photoelectric effect. We have the Survey Conference in 1927. But still, Einstein has been working on the theory to show that there should be something which was more than quantum mechanics. And then, in 1935, with two collaborators, Einstein published one of the best papers in physics. This paper was published with Podolsky and Rosen. And before being published, this paper was anticipated by the New York Times with the article that you can see in the slide, which title is Einstein's Attacks Quantum Theory. So this is strange because Einstein, I repeat, was considered one of the fathers of the theory. So seeing one of the fathers not accepting all the consequences of the theory was really anomalous. And the article that you can see here has the following title. It's a beautiful article. It's one of the articles more cited in physics. And the title is, Can Quantum Mechanical Description of Physical Reality be Considered Complete? And you can also see that I here report the consequence of Einstein-Podolsky-Rosen. While we have shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. Why I want to put all this emphasis on this article? Because in this article, Einstein tried to demonstrate that the theory has some limitation. And to this purpose, Einstein discussed for the first time the concept of entanglement. Now, our conclusions are completely different. Entanglement is not a limitation of quantum mechanics. It's one of the key features of quantum mechanics. And entanglement is the ingredient which lies at the heart of the so-called second quantum revolution that we are going to discuss later. So now it's time to see what is entanglement. So let's consider the argument done by Einstein, Podolsky, and Rosen. The concept of entanglement. Entanglements, it's a word which identify in English when two systems are highly concatenated one with the other one. In Italian, it will be aggrovigliamento. In Spanish, entrelazamiento. It means really two systems that cannot be disjointed. So let's discuss this entanglement. We consider two particles, which calls these two particles A and B. We have two particles, and then as you see now in the slide, I consider the particle A to have two features. So let me maybe now remove a bit, 1 second the slide, and then I will go back to the presentation. We consider two particles. We have particle A. This can be a photon, for instance. This particle is quantum. This means this particle will be described by a wave function. And for this particle, we consider a physical feature which is dichotomic. Dichotomic means that this physical feature can take two values. For instance, the value 0 and the value 1. I repeat, the prefix A stands for the particle, and the state 0 and 1 describes the feature of the particle. This can be the polarization of the light, the position, and something else. We have seen that the particle is quantum, the photons, and then if you have a state 0 for the particle A and also state 1, since this is a wave function, you can also have the state 0 plus 1A. You can combine the two, as we did before with the photon, which was propagating along the path A and the path B. And this is if you have only particle A. Then we consider a second particle, particle B. Again, that will be a photon. Again, this photon will be quantum. And we can describe a physical feature of this photon, which is dichotomic. Again, this can be 0A, B, and 1B. And then you can have a state which is a 0B plus 1B. So let me try to provide you what can be an example of the feature of the photon. Sorry, I'm fighting with my slides. Okay. Which feature are we considering? We are considering the polarization of light. So let me describe you what is the polarization of light in a couple of minutes, only to provide you an intuition. So we know that light is an electromagnetic field. So light propagates as electromagnetic waves, which oscillate. I'm here representing the electric field. You can also have the magnetic field. These are waves which propagates, and you have the electric field which oscillate, and the magnetic field which oscillate. Now, what we call the polarization of light is the direction in which the electric field is oscillating. So if light is going in this direction, and if the electric field is oscillating along this direction, we will say that the polarization is vertical. Instead, if light oscillates, electric field oscillates along that plane, we will say that the polarization is horizontal. Let me write this. So we will have horizontal polarization and vertical polarization. This is what happens when you have electromagnetic waves. If now you have a single photon which has a polarization, you will say that if you have a single photon, let me write this here, one photon per time, we will write down that if the photon has polarization which is horizontal, it will be described by the following wave function, where H stands for horizontal. This wave function represents a polarization, a photon which has horizontal polarization. Then you can have a single photon which has vertical polarization, and the wave function will be the following. And then you can have a single photon which has a superposition of horizontal plus vertical polarization. And this will represent a single photon with a polarization at 45 degrees. We will write this state as plus A. Let me comment this in a different way. You already have studied at high school what are vectors. And you learned when you have studied vectors that vectors can be linearly combined. You can take this vector, and you can do the sum of the two vectors and you get this vector. What you are doing, you are linearly combining the two vectors. This is analogous with what happens when you have a wave function. You have two wave functions, horizontal and vertical, and you can then combine these two. I would then suggest that if you have any questions, it's now a good time for questions before we go back to the concept of entanglement.
Okay, yes, a few questions. So first of all, there is maybe a naive question, but if you can clarify this notation, strange notation with the cat, I mean, with this, how do you, they are probably not used to see vectors like this.
So let me, thank you for the question. This is very useful because now that I have my tablet working, I'm still trying to find where is my mouse. Okay, and we try now to, okay, my mouse is there. Let me try to clarify this. Thank you for the question. So I've told you wave function, okay? With a wave function, this is how we describe a quantum system. And to this purpose, we adopt the following symbol, which is called cat. Not a cat, that's the way we write. This is a symbol. And what you write inside here, inside the cat, this is the state of your system. For instance, let's summarize. Today we have seen, I have adopted this symbol already many times. Let's see some example. I adopted it to write down photon in A plus photon in B. And this was a way to identify that your system was in a quantum superposition of the photon propagating in A and the photon propagating in B. This is the first example. A second example is how you describe one particle, one photon, which has an horizontal polarization. You write this in the following way. And how you describe one photon which has a vertical polarization, you write this as follows. Danilo, I hope to have clarified very shortly the questions.
Yes. So then another question is, if a quantum mechanical system can be simulated, and in this case, what is the space size needed to save the information of a piece of quantum reality? This is a very precise question from Cometa.
This is an excellent question, which anticipates somehow what we will see later on. Cometa will answer you briefly, and then we will see. The point is the following, that you can write down the wave function of a systems composed by n particles, but this is, you need a huge space. Let me answer this. But then I will answer to this then later on, but I don't want to simulation of a quantum system. So the answer that you can simulate a quantum system, because when you do simulation of chemistry effect, when you investigate particle physics, you are doing a classical simulation of a quantum system. But this is very challenging, because if you want to simulate n quantum particles, you need to have systems, you need to have a classical systems with a dimension of something like 2 to the n. This means that it becomes exponentially hard to do a classical simulation of a quantum device. And I will come back to this point later on during my presentation. This is a very excellent question. Thank you.
Okay, then Torie asks, why you divide by the square root of 2?
This is a very good question also. Obviously, I'm really trying. Quantum mechanics is tough. It requires a lot of mathematics. So my goal today is only to show you a bit an intuition on how it is beautiful conceptually, and also how it has some huge potential from the technological perspective. Why do I use, your question is, why do I use the square of 2 in my symbol? And the reason is that I need to normalize the wave function. Say in a different way, is the sum of the probability of all the possible alternatives should have a sum equal to 1. So you can say that if you sum different probabilities and you have a partition of all the possible events, the sum is always equal to 1. And this is the reason why I have this normalization factor. We can now neglect it because it's something that you need to have a self-consistent theory which predicts correctly all the results. So Danilo, do we have some?
Yes, there are a couple of questions about how two particles become entangled, or how can we create an entanglement.
Perfect. We are back to the next slides. That's exactly what I need. Thank you. So let me summarize only before I go back to the presentation. Let me so 1 second only. I need to do some to add some slide here, and I will get to you. So before I go back to the presentation and we go back to entanglement, let me summarize the experiment. We have photon A, photon B. These are two quantum systems. And I'm interested on analyzing the polarization of this particle. photon A, I will consider 50-50K, horizontal and vertical, and photon B, horizontal and vertical. Another way to label the state will be not as horizontal and vertical, but you will see my slider, we call this 0A and 1A, and this as 0B and 1B. So in my presentation, 0 will stand for horizontal and 1 for stand for vertical. But now we go back to entanglement to answer your question. So let me see again what is entanglement. We have the two particles. And on what we see in the slide now is a case in which particle A has horizontal polarization, while particle B has vertical polarization. But then you can also have the opposite case, where now particle A is vertical and particle B is horizontal. This was one case, the other case. But now we are in quantum mechanics. We can have a superposition of these two possibilities, and we add a plus. And this is now an entangled state. So plus or minus is the same. So now you see a minus, but it's pretty similar than having a plus. So what you have now, you have a superposition states, not of one particle, but of two particles. These two particles are now entangled. And this is very counterintuitive because now the feature of one particle are connected somehow with the feature of the second particle. And this is entanglement feature. So this is a way to represent it conceptually. These two particles, which are entangled independently on how far apart they are. Schrödinger, one of the founders of quantum mechanics, named entanglement not one of the features, but the characteristic trait of quantum mechanics. The characteristic traits which clearly show how quantum mechanics is something which is fundamentally different from classical physics. And what is the peculiar aspect that when you have entanglement, you can have the particles which are far away and still they exhibit this very strong correlation, which is entanglement. The question was, how can you generate entanglement? In order to generate entanglement, you need first to have the two particles together. You need the two particles to interact. How we create entanglement? In our labs, you have this animation. In the center of the animation, you see a crystal. You send a laser inside this crystal. The laser is represented by this blue ball. And inside the crystal, one of the photons of the laser, one of the blue photons, is dividing, is decaying in two photons, the red one. So it's essentially one particle which is splitting in two particles. And now these two particles, the red particle, if you use a very peculiar geometry, they can be created in an entangled state. So this is conceptually, this is a picture of my labs in Rome, where you see a standard apparatus that we adopt to create entangled photon pairs. So let me now show you. So I don't know if you can see the mouse in the screen. In the center of the picture, you have a crystal. In this crystal, we create the entangled photon pairs. So you see a violet here on the top side of the picture. This is the laser which is exciting the nonlinear crystal. Inside this nonlinear crystal, you create a pair of photons. So if you see the laser, here you have billions and billions of blue light, while you create only few pairs of entangled light. So this means that you have here few photons coming on these directions and few photons coming on this other direction. And now with these red arrows, I'm representing the direction in which these two photons are created. How you create entanglement? You need to have the laser, the crystal. You also require a very peculiar geometry which allows you to create the entanglement. And after that, to have created entanglement, so two photons can be injected in some fiber, and then they can be sent to some experiment that we are carrying on. So here we have some slide. So entanglement has been observed for the first time now 20, 30 years ago. But now, what entanglement tell you when you create entanglement in the labs is that entanglement is something which is completely different from classical prediction. And so you can imagine that entanglement it's a kind of quantum resources which not only has a very fundamental implication, but which can also exploited from a technological perspective. Then I guess this is now a good time for question before we try to move from the first quantum revolution to the second quantum revolution.
Okay, so there is a very almost maybe philosophical question from Angelo, very interesting. So, can systems made by entangled particles can be used to carry information at a speed higher than the speed of light?
This is an excellent question. The answer is no. Many physicists tried to exploit entanglement to have superluminal communication, but the answer is not possible. This is very subtle. So let me try to go back to the slide and to try to answer your question, which is very fundamental, but which requires some logistic support to be answered. Let me add one more slide here. Because the way in which typically entanglement is described in the mass media is often wrong. So often entanglement is described as an instantaneous action which is connecting A with B. It's much more subtle. Because imagine to have two particles, A and B. And imagine these two particles to share an entangled pairs. This means you have a particle here, and the wave function of these two particles is an entangled state. Like the one I'm just writing. This state brings unique correlation, but being correlated does not imply that you can have causation. This means that if you do an experiment in A and an experiment in B, the way in which the experiments are correlated cannot be replicated by any classical theories. But this is different from saying that A can transmit information directly from A to B. So I would say that there is a big difference between correlation, which is what you have when you have entangled photon pairs, and causality. Causality means that A can directly send some information to B, while correlations means that A, I'm sorry, I moved to while correlation means that A and B may have common sources which makes the two results correlated. Summarizing with entanglement, you cannot have superluminal communication, but the correlations that you observe cannot be replicated classically. This is my answer in few words.
Okay, good. Maybe we can do the last one, then we go on. So I joined together two similar questions that are, how can two entangled particles become, if they may, disentangled, and if we can entangle more than two particles?
Excellent question. So let me go again, I need some slide to answer your question but I prepared not enough slides backup, so I'm adding one more, and we are ready to answer. The first question is, can we have entanglement between two particles? I write down again this state, which the state is entangled. How we can then entangle it? It can happen because you may have A and B. And for instance, if you observe A, you do a measurement on A, this will partially reduce the entanglement between A and B. So you have two ways to lose entanglement: by local observation, depending on which you perform, and also if you have an interaction with another system. And this was the answer to the first question. The second question was, can we have more particles entangled? Yes. Imagine that we have three particles, A, B, and C. Then you can have an entangled state of the following form. This state is called GXZ state, from who invented the state, which are Werner, Horner, Zeilinger. And then you can extend this to n particles. And what is interesting that when you increase the number of particles, you may have many different kinds of entangled states. You have a zoology of entanglement. Not only, but the more particles you have, the more is a discrepancy, the departure between quantum and classical. And while when you have two particles, there is only one kind of entanglement. When you have more and more particles, you have many ways many particles can be entangled. And this was my answer to the second question.
Okay, very good. So other questions are coming, but I propose, since we have 15 minutes left, to go on, if you agree on your last part, and then maybe we can have another question time at the end.
So up to now, thank you, Danilo, I focused my attention on two ingredients. One, the superposition principle. It's fundamental because if we don't grasp it, we cannot see what are the potentialities. Second, entanglement. Why is entanglement relevant? First, because of a fundamental reason. And then because entanglement tells us that this is a way that on which we can, we have a strong departure between classical and quantum. Now we have 10 minutes left, and then we want to jump on the second quantum revolution. What is the goal of the second quantum revolution? To exploit the superposition, entanglement, in order to have a new technology.
We're at the beginning of the second wave of the quantum revolution. The results of the first wave are all around us. And now, quantum technology is ready to take us even further. The foundations of quantum physics were laid a century ago in Europe. Here, famous scientists paved the way for the first wave of the quantum revolution. Groundbreaking technologies arose that have changed the way we live our lives. 100 years later, Europe remains at the forefront of global research efforts. Around the Union, researchers are working to unlock the full potential of quantum technology, to contribute to global challenges for better healthcare, clean energy, and new materials, to provide safety and security solutions, and to seed unimagined possibilities in the future, resulting in a more sustainable, more productive, and more secure world. In order to catch the second wave of the quantum revolution, it is vital that Europe joins forces and acts now.
So, So this was somehow a summary of what we have seen. Quantum mechanics is at the heart of many devices, but what we want now is really to fully take benefit of all its features. And the ingredient is called now the qubit. So to know the concept of a bit, what is a bit? It's a basic unit of information. It's the way in which we encode communication and computing. A bit, it's a Boolean variable, which can take the value 0 or 1. What is now a qubit? It's simply the concept of bit moved in the quantum realm. What will be a qubit? It will be a system which can be ket 0 or ket 1, but since now it's a quantum system, you can also have a quantum superposition between 0 and 1. If you want one example of qubit, it's a photon which is propagating between the two paths A and B, which was our starting point of today. What we want to do now, we want to develop a technology where we can manipulate information exploiting qubit. Why we want to do that? Let me. You may have several fields of application. Up to now, we discussed basic science, entanglements, and superposition. But then you can also have many fields where we try to exploit quantum phenomena in order to improve your technology. And this field can be communication, computation, simulation, but also sensing and metrology. So now what you see in these slides, is somehow how you merge quantum mechanics with the theory of information. So on the red part, on the top of the screen, what you see is all the features of quantum mechanics with all the different subdomains. On the downside, in white, you see the theory of information, which is the theory behind computing, behind cryptography, and behind simulation and so on. Quantum information is a field of research and technology, which is at the forefront between the field of quantum mechanics and the field of the information theory. Now, if you want to do quantum information, you need to have a technology where systems are behaving in a quantum way. So at the center of the slide, you have the domain of application, while on the corner, you see all the different technological platforms that you can exploit in order to carry out quantum information processing. In the center, there is white and single photons, which was my previous example, but you can also have the different of hardware. You can have ions, which are trapped one by one. You can have superconducting qubits. You can have atoms, which are trapped via some laser field. So, I mean, there are different directions of interest. This can be communication, but also computation. Since I'm a bit short of time, I would like to only show you now something more on the communication side. We discussed it before, the polarization. I've told you how you can have light which is entangled. You know, one can wonder, but is this observation of entanglement something that you can do only on the lab? Or is today's technology developed enough to move this concept out of the lab? And to answer this question, I would like to show you one of the most advanced results on entanglement, which was obtained by China a couple of years ago via what's called the Michel satellite. The Michel satellite is a satellite which was able to create entangled photon pairs while in the orbit, and then to distribute these entangled photon pairs from the satellite to different background situations. And by using this satellite, they could exploit entanglement in order to carry out cryptography with a unique approach. So let me show you now
the quantum experiments at space scale, which has demonstrated quantum communications over 1,200 kilometers between two base stations in China, wire to Bob, and Bob would receive those in such a way that they could then figure out the messages were used for each photon. So Alice tells Bob what she sent the data as. Bob tells Alice what he listened as, and now both of them know which ones match up. So they can throw away all the photons where they didn't agree.
So the key point that using entanglement now, you can test of quantum physics in the orbit, and you can also exploit now these results in order to do cryptography in a really unbreakable way. Since it is now 11:40, I won't have time now to discuss more about the quantum computing side. I would like the last couple of minutes only to show you one slide, which was how recently Google could achieve a regime where they could perform one calculation, useless, but still better than with any other classical counterpart. And then, as last comment before the last question time, I would like to really go back to the foundation side, where you have on one side the macroscopic world where we live, where we have the classical physics rule. On the other side, we have the microscopic world where we have quantum physics, where you have particles. And then you have a kind of boundary between these two perspectives. And so you can have this kind of summary where you see on the right side our trivial everyday life, and on the left side our quantum features, where you can have like a cat which is live and dead at the same time, where the smoke can move along the two paths. And now somehow trying to develop a quantum technology is somehow a way to try to move this boundary to make the quantum effect available on a larger and larger scale, and in a way to perform computation with quantum systems and so on. So I don't have now time to go back on more fundamental issue. So I guess now we can have the last question time, since we have 5 minutes left.
Okay, yes, we have time for the last two questions. So one is again about entanglement. So Leonardo asks you, if we have two particles that are entangled, for instance, by polarization, what happens if the two polarization of the two particles are measured exactly at the same time by two different observators?
So let me imagine we have the two particles, A and B. If I measure A to be vertical, B will be horizontal, and vice versa. Now, your question was about the time. What is the role of the time on the entanglement? This has been also investigated experimentally, for instance, by the group of Nicolas Gisin in Switzerland. And it turns out that what you are observing at the end are only correlation. So there is no defined order on whether you measure first particle A and then particle B, or vice versa. This is a prediction, but this prediction was also tested experimentally with a very subtle experiments. So the question is well posed, but when we talk about correlation and quantum mechanics, it's not trivial to understand what is the role of the time.
Okay, thanks, Fabio. The very last one is this. If we disturb reality with our observation, how can we prove anything? This is very interesting.
One of the big questions is about the wave function. So what is the wave function of a particle? Is the wave function a mathematical tool that we adopt to describe reality? And this is what we call the epistemologic interpretation of the wave function. Or is the reality, or is the wavefunction the reality itself? So psi, my cat, this is the reality. And this is the ontological interpretation of quantum mechanics. It's very hard to do an experiment to verify whether one interpretation or the other one is the correct one. But I would add that recently, some very specific experiments have been devised which some under assumption can test whether the wavefunction is real or not. So this is a very fundamental question. We don't have yet a complete answer. Some answer relies more on the interpretation of quantum mechanics, but we can still go on highlighting some features of the reality and how to conciliate reality and quantum mechanics.
Okay, thank you very much, Fabio, for this very inspiring and clear lecture about the amazing quantum world. So I also thank you on behalf of all the students, and we will try to ask to answer offline to some questions that we didn't have enough time to answer to now. And so this lecture is finished, and I want to remind to all the students that at 12 o'clock we will have another lecture about the nature of time, another very inspiring and interesting argument. So Fabio, thank you again, and see you.
Thank you, Danilo. Have a nice day to everyone. Goodbye.
Bye.